everybody. We're lucky to have Antoine Kouchner today.
Please go ahead. Thank you. Hi everyone, I hope you can hear me fine. With the case. It's a pleasure to be here. And I would like to thank the organizer for this invitation to speak to you about the ANTARES adventure. I hope that my talk will not sound too much like an obituary. It's not the goal. I rather try to enjoy a good digital adventure time. So I'm going to tell you a story, which is the one of the ANTARES adventure. So I will tell you about the sector, if you don't know what it is. And then of course try to go quickly through some of our scientific results before I mention what we plan for passing the battery. So this is okay, so the ANTARES telescope has been located offshore in the Mediterranean Sea, close to the French Riviera, close to the city of Toulon, like 40 kilometers away on the shore, on the island of Port Royal that you can see here. And so it was really a very nice place where to exploit a detector. It's actually here you can see the cable that goes from the detector location to the shore station, what we call the Institut Michel Pacha, which was probably one of the most beautiful floating rooms in the world. You see here the building, and we are still installed here. These are the rooms from which we monitor the detector. So very a nice place to be, especially if you are in the deep underground detector laboratory, then you would expect data. I think this place might be some location for you, if you consider. And of course, once inside, you have one of the best views that you could dream of on the on those windows actually on the other side. So this is the view that you have from the county room. A very nice place to be. But at the end, things were very fine, and of course, we were doing remote shifts. So good. But we were not always inside. So the detector sketch is here. You know it, I think. So ANTARES was a small detector, a small neutrino telescope with only 12 screens and a total of about 900 EMTs distributed through the screens on stories. And the stories are shown here. 3 optical modules, large EMTs on each story, and a container for the electronics. Each of the screens were connected to a main junction box, and the cable I showed you earlier was connected to the junction box and to the shore on the other side. So this is the distribution of the tower, and all the data from the screens passes through the main cable. And in order to connect these things to the junction box, we had to use submarine behaviors, and I will show you some of the details. So the completion of the detector was in 2008, and we just started coming back to that. So one of the questions what you may ask is why do we need water in the deep sea, which is a quite hostile environment in order to exploit detectors. So the ideas came, let's say, as early as in the mid-70s with the first experiment that was called the DUMON for deep underwater muon and neutrino detector, which was originally planned to be built in Hawaii, which is maybe also a nice place to be actually, if you want to with the counting rate. Never been there though. Unfortunately, after various efforts, prototyping, the project was not funded, failed because of essential failures due to water ingresses, which is the most difficult part to handle with such a detector, and the project was terminated. And to tell a very long story short, I could say that there were then 2 paths. One that was the one that followed the Ice Cube collaboration to move to the South Pole and build a large detector there, whereas the success that you all know, of course, things are more to some extent as easier to deploy there once you get to the South Pole, because you then essentially have to dig a hole and then put your screens there, and then after the water freezes again after a few hours, and then of course this water ingress issues do not remain over the long time. So, but other people continued the efforts in the deep sea, and that was essentially in the Mediterranean, the Nestor efforts. I'm not sure you see the pointer, do you? Or it's used to it, yeah. So the Nestor effort, so the idea was that at that time to build large towers and to put these towers into the deep sea. But this also was not a relevant way to go because it's very difficult to handle large structures, and this project was not very much successful. But why do the people wanted to continue in the Mediterranean Sea? This slide summarizes to some extent the effort. One of the reasons is that the deep sea has long and rather homogeneous scattering lengths, and that provides good pointing accuracy. Also, you have access to deep sites to protect against the atmospheric background, very close to the shore. And then you have also the logistical infrastructures that are very easily accessible close to the shore as well. Then, of course, since there was a detector being built in the deep, in the southern hemisphere, the idea was to complement the field of view staying in the northern hemisphere, and therefore to have access to the full sky. The animation that you see here has been provided by, I think, an ICU member, Claudio Copper, I think, a long time ago, and this is a simulation of a high energy muons passing through the detector, the same detector, in seawater and in ice. And the red things, patterns that you see are actually the lights traveling, Cherenkov light traveling straight to the PNGs in seawater, while in ice you see the scattering phenomenon, and of course this affects the pointing accuracy. But another advantage of being in the Mediterranean Sea is that you are in a mild latitude, and so you can take advantage of the Earth rotation to scan a larger field of view over the day, right? And so therefore you can have some part of the sky that complements the others. And with that, you may do on-off studies because you don't see the same part of the sky all the time, and so we can characterize accurately the background of specific zones when you're not looking at the source, the specific one. There's a drawback, of course, which is related to the optical background, because our detector are optical sensors. There are salt, of course, in the sea, and then you find some potassium. It's potassium 40 decays, it's radioactive, and it creates electrons providing Cherenkov light all the time. But it's actually quite useful for the calibration, though it requires some. I will tell you about this. So in 1997, we proposed the ANTARES detector. So this is the proposal. And so you can take a look at this quite old document. To make the long story short, between 2001 and 2022, this is what we have been doing. So in 2001, we have used the Nautilus submarine, which is quite known. Some of you may know the planet story, and this has been used to recover some part of this. So this is the manned submarine vehicle from Kouchner. And this is the same in 2022, so it has been refurbished to some extent, but it's the same vehicle. So in 01, we installed the main electro-optical cable, and then we placed the junction box in 2002. In 2003, we had a prototype sector line. In 2005, we had a mini instrumentation line with this time optical modules. And then we had our first complete detector line in 2006. Then the full detector was completed in 2008 with these 12 streams. And it has been running up to 2016, when in principle, we had to stop that. But we decided that the field was so blooming, so exciting because of the results of IceCube and also the multi-messenger endeavor, the followers of gravitational waves, that we decided to prolongate the data taking with no running cost. Essentially, we only had to pay for the electricity bill that was amounting for to 20 kilo euros per year. So this is all what the Institute had to pay from 2016 up to recently. So very, very cheap experiment once we okay, so then we stopped the data taking into recently because now Plenary, which is the successor, is ready to take the torture. So these are the main steps. So you see pictures from the main electro-optical cable in 2001 being deployed. So of course, this is the beach of the Savlet. Usually you go to take a bath, but this time they have to work on it. So this is the boat that we use to install the main electro-optical cable. Then you see pictures of the construction of the junction box. So the core of the junction box with its electronics, and then you place this into an egg-like structure. And you see this junction box with the egg that you recognize here on the board. And on the other side, you have a panel where you do the connection of each of these things. So this is in 2002. I'm also showing you these pictures not because I said it was a very, very nice place to be. It's not always the case in the Mediterranean Sea. There are harsh conditions as well. And I think sometimes there are hard problems in performing the installations. I was once a bit sick. Fortunately, we get back before we had to do any deployment. So this is a recent picture of the junction box after we deconnected all the cables. So this was the recent. So it worked reliably for 20 years, no failure, no repair needed. It's still done in water. It's waiting for a potential recovery for the future, or maybe a second one. We'll see. So this is a picture of the first complete detector line in 2006. So you see the different stories. You see the buoy, and of course the anchor would be on the other side. So it's easy to recognize line one because it was deployed on the Valentine's Day. So some of the people on the boat decided to put this art, and actually it's amazing because it remained. So this is the picture from the connection in 2006, and this is a picture from the disconnection in 2022, but we know that it's line one because of this here. Although we have other ways to know that it's line one. And so this is a picture from May when we recovered the chain, and so it was a very peaceful weather. And so you see the different floors here that are aligning, and maybe you see here there is the buoy that you can recognize by the yellow color. And so we recovered all the stories, as you can see here. And of course, we now place them into some boxes, and that's it. So this is now line one back to the shore after so many years. And so then we cut the pieces, and then, okay, we are going to make use perhaps, or perhaps not, of some of the elements. So we had a long monitoring of the efficiency of the detector, and I was mentioning earlier the K40 that we use. So in fact, if you with different PMUs on the same floor, you can try to see coincidences as coming from the K40 decay, the electrons impairing the Cherenkov light. And so by looking at the coincidences, the placement of the peak, you may adjust the time, of course. The width of the Gaussian that you find gives you information about the resolution, and the amplitude of your peak gives you information about the efficiency that you can then draw along the time. So this would be the overall efficiency of the detector from 2010 up to 2020. And so we have done this regular efficiency monitoring, and overall we had somehow 20% of efficiency loss. And so this is quite moderate actually over the full period of the detector running. And I think K40 is indeed a good way to calibrate the detector. So I think you know the detector, the principal detection. So this is the detector. You look at the dial. This would be a long track inside the detector. This is the track channel that provides you with the best accuracy on the pointing. Depending on the angle, you will have access to TV and more horizontally to PV energy. But okay, this is too well known. If you're looking at cascades, which is essentially not code of Cherenkov light, but rather a spherical light that because of the dimension of the cascades or the electrons in the detector with respect to the PMT adjustments is small. Therefore, you see a bright point, but the direction of the light remains, at least in the seawater, because of the scattering conditions. And so you can use these topology as well for astronomy in water, and then this provides you with a sensitivity to all neutrino flavors. So this we have been doing, and these are the performances that we got for the tracks against the energy the angular resolution that is better than 0.4 degree for energies above 10 TeV in the track channel. And for ANTARES, it was better than 3 degrees. And this was the first time that we use this in the deep sea. It's a bit better for kinetic, but there will be other talks about this. So the silent scope that we wanted to tackle is actually quite large, with an energy threshold of about a few tenths of GeV. There is the possibility to study the oscillations, neutrino oscillations. That was not the main purpose of ANTARES. Dark matter searches in an energy medium range between 10 GeV and 10 TeV, looking at excesses in the direction of dense body where wind would accumulate and either decay or annihilate. I'm not going to cover this things as a whole. And let's search for extraterrestrial sources of neutrinos. That would be the goal related to the question of the origin and production of high energy cosmic rays. We could also do some kind of exotic physics, searching for monopoles and nuclides. We have to be in surface. But more than that, because it's deep in the sea cable monitoring all the time, ANTARES was a pluridisciplinary observatory, and Kouchner will be even larger one. And we had communication on different aspects of physics. And so if you're interested, you can take a look. For instance, I will tell you that we have monitored with different instruments one of the conditions of spring blooming optical activity in the deep sea. We draw conclusions that sometimes the blooming activity in spring comes with the fact that we had cold winter. The cold winter will make the surface temperature weather quite cold, and then it will sink in the deepness, bringing oxygen and the sediments, and if because of that, it will propagate in the deep sea, and then you will have conditions of high blooming activity in spring. So this is not very good for us because we don't really want to have more and more optical activity, but I will be better for our colleagues. Also, maybe good news is that we could study with our devices for recalibration the acoustic monitoring of the deep sea, and we have seen different behaviors for sperm whales, for instance, and we concluded that first of all, they seem to be rather safe and present, and also, if I understood the data, they seek to feed and imitate just like us. Okay, so if you're interested, you can take a look. So at low energy, we study the oscillations. I'm going to be very quick. So this is the oscillation pattern that you would expect for vertical outgoing muon neutrinos. And the different curves tells you how you will be sensitive in case of if you add some sterile neutrino, for instance, if you change the parameters. So essentially, we were sensitive to the deep here at the most 24 GeV, and the deep will reduce or be displaced with different conditions. So with that, we were able to make a first measurement of the oscillation parameters, which is not very competitive. It's the black line that you can see here, but it's consistent with the worldwide measurements. And we excluded the no oscillation hypothesis up to 4.6 sigma with the same sample, and because of the curve that I'm showing here, we do try to constrain the possibility of additional neutrino species as there are neutrino. And so there's a tight complementarity here, information with the EV scale neutrino experiment searches. And so our results exclude regions of the parameters that were not yet excluded in the picture. And you can also, along the same kind of things, try to look for deviation from the oscillation pattern that could be inferred because of non-standard interactions. So our constraint on one of the non-standard interactions that we can see on this plot is along the demonstration dates. But okay, I have no time to dig into the details about this. As I said, we extensively search for dark matter, but this will be mentioned by Rebecca Levens in this conference. So I refer to you. I ask you to go to this part if you're interested. And then just let me show you the limits that we currently have on magnetic monopoles and nuclides. So it's a bit distinct, and maybe it's confusing to put these things on the same slide because nuclides are such as downgoing particles, by monopolarized search are outgoing particles, but the common thing is that they emit a band of light in principle to the detector, and so you can constrain things here, and our is now interesting with respect to the continuity. So for high energy, we search for a diffuse flux. Try to see if it will be sensitive to the ice cube flux observed. So we did that with the track sample, the shower sample. What we see is that we do have a small excess at higher energy. So you see here the data, the red curve shows you what you would expect from the cosmic signal of ice cube. So overall, we have 58, we were expected 36. So it's nothing very significant, but it means towards the confirmation of some excess at high energy. If you turn this into a signal and you treat this, then you have the contours that we could achieve in terms of spectral index and normalization. So these are two different ice cube best fit depending on the sample used. This is ours, and you can see the contour. So this is not constraining, but it is compatible. And if you draw the plots against the energy, so this butterfly, the ANTARES one, is the pinkish one, that of course with much larger levels. So now if you search for diffuse fluxes into a reduced region, you start to be more sensitive, obviously, and we did that together with ice cube, searching for the galactic plane. And so I think what is interesting is to show you the contribution to a potential signal of ANTARES and ice cube combined in terms of inclination. So the red is the ANTARES track, and the orange is the ANTARES shower. Ice cube is shown in the review. And so we have combined things, and we came to the conclusion that there should be a small contribution of the ANTARES of the ice cube diffuse flux coming from the from this galactic region. Updates are coming about this. So reducing again. So yeah, we did that about our own actually. Also, as I mentioned to you, making on and off studies. So here you see in galactic coordinates, you see the on region, which is this rectangle. So we try to avoid the Fermi bubbles, and you see all the off regions studied in the background. So we still have to work on that, but our sensitivity is shown here. So the black crosses or black data are the Fermi one, and so it indicates important spectrum. So this will be the sensitivity of ANTARES in black, and so we should be in a position to constrain the possibility of a cutoff or no cutoff or a hard spectrum as coming from the galactic plane. So this should be updated soon. Okay, so we went to close to smaller regions of the sky. We combined also again with the ice cube point source. We couldn't find any so far. This is not the latest. It's not the latest plot, but just to tell you again the good complementarity between ice cube and ANTARES. So the blue are the ice cube 7-year sample sensitivity. ANTARES here on this plot is in red, and the combination helps gaining a factor of 2, depending somehow on the spectral index that you choose. So our latest point of search is shown here. It was done with all flavors. So again, you see our sensitivity against declinations, and all the plots, the dots are specific sources that we looked into. So it's interesting to see that, okay, when you are well removed the sensitivity, it's because you have a small excess. None of them is significant for the time being, but you recognize some of the known sources in our data, for instance, the excess of 506, which is one of the most significant sources we have in our list. And we also search in the whole sky. So for the whole sky search, we had the most the hottest spots is located here, where you see the red arrow, but it's not very significant. But it's also less than 1 degree apart from this most significant source that we have in the predefined this source, which is this PKA source, which has a post-prior significance of 2.57. So, you know, nothing extremely interesting, but still. We also search for catalog-based searches. An interesting result that we find is when we use radio galaxies, but we're still working on that. And so what I'm trying to tell you here is that based on this Plenary paper, we are launching study, and in principle, we should be able to constrain, so this would be our sensitivity, a large fraction of these, of the ice cube diffuse flux as coming from radio sources by looking at catalog-based pieces. Okay, we have a very aggressive multi-messenger program in two ways. First approach is to receive the alerts from external figures and to look into our data. We made that for several cases. The most famous one was the search for a counterpart to the GW17OX17 events. This was done in conjunction with other experiments, and we couldn't find a signal. We've done that actually with all the potential multirational wave levels, including black hole mergers. Nothing came to a signal, but we did it in a systematic way, and we started doing it as well with ORCA, which is the low energy range of chemical entity. So this one is actually an ORCA plot for some of the same sources. Of course, we were interested in following Ice Cube 1709-22 event that triggered the discovery of TXS. And so for that, I think it's interesting to update you on what we find. So as I told you, TXS appears to be one of the most significant sources that we have in our list. The updated results with recalibrated sample gives us now 4 atoms within 1 degree on the source. So it's we feed 2.9 atoms and it has a peak higher of 2.9 sigma. But we are going to investigate further into this with the final sample. We also look for other interesting events from Ice Cube, the TD events that you've heard about and we're going to hear maybe about in the next cohort, or if you went to go parallel sessions. We couldn't find any counterpart to these sources. The second approach is to launch your own alerts. Once you have very interesting events in hands, you want to tell the community and to ask them for follow-up. We've done that with many instruments in a wide ranges of wavelengths. So this is the summary. There was nothing spectacular. We had once, we were very much excited. It was in 2059 in September, because once we get an alert, it was very activity in X-ray. And so we had a hope that we had a discovery after many inquiries and multi-frequency observations. It turned out to be a spurious association with a star, which is very unlikely to be the origin of the neutrino. So now we're moving to CamFiNet. It's the successor of ANTARES. So CamFiNet is going to be with 2 branches. ORCA is dedicated to oscillation, and ARCA is dedicated to astroparticle physics. So ORCA is going to be dense, ARCA actually to be sparse. One is mainly one building block, and the other one has 2 building blocks. And so we build on ANTARES, as we considerably changed the design of the experiment with small PMTs in a similar glass sphere on which we can gain many advantages. But I have no time to tell you more. Only one thing about ORCA, we do expect to measure the mass ordering of neutrinos after 3 years, whatever is going to be theta 2-3, and whatever will be this mass ordering. So this is our goal. So this is, I'm almost finished. This is the successor of ANTARES, the map of the collaboration. Recent good news, ORCA has 10 detection units deployed, and ARCA 19 detection units deployed, and I think you'll have details from Hazard in another talk. But we had a speed record recently established. We put 7 DUs unfurled in less than 48 hours. So it's really important to gain time with respect to ANTARES if you want to put so many strings in the weapon. So we have compactified strings and they unfurl by themselves so that we have time. And another important news is that we have 67 million euros budget approved from Italy. So we have now enough money to build more than half of the detector, so a full building block for ARCA as well as for ORCA. So in conclusion, this is the post that we recently put on the ANTARES website. ANTARES has been fully dismantled. We recovered everything. And this picture is actually one of the prototypes for CamFiNet that we put on one of the ANTARES strings, so you recognize the multi-PLT things. So ANTARES is history now, and we hope that it will continue with KMT nets. So I think that we made demonstrations that we can exploit deep sea telescope. And now the adventure is not over. In fact, we have still 2 years of data to analyze, to provide to the community a sample that can be reused by anyone. And in the meantime, I hope that you can join forces with us in the candidate for the next endeavor. Thank you very much.
Okay, well, that's really nice story. I'm very inspiring. Are there any questions for Antoine? Yes, go ahead.
Could you back to the slide where it's like the pre-trial and post-trial probabilities?
For the consources,
Yeah,
it's when you're referring to.
it's got a table of like, and maybe you need to go to the figures to explain my question. My question is just, how are these? Yeah, how are these computed? Is this for like one event or
No,
few
so-
events?
So this is a catalog-based search. So we're trying to associate our neutrino sample with known sources in a log likelihood approach. And so we do this, and then of course we make pseudo experiments in order to compute the trials that we have to do. So this is essentially the way you would compute the post-trial significance. So as you see, there's nothing really significant, but we have a hint with the radio galaxies. But sometimes, since you're looking at different sources, of course, you can actually take a look at which are the dominant sources that drive the smallest p-value that you may found. And it was the case actually for this Fermi catalog. It was mostly this source. It's interesting because we also communicated with IceCube that when you look at the sharing time of these levels, we had we spotted an IceCube level during a flare, and so combining this is more. Okay, it's not a question.
Yeah, thank you.
One question.
Thank you for the next one. Could you go to slide 27, please?
7,
27.
27. Okay.
Yeah, so I was wondering whether we fitted both tracks and showers at the same time.
Right.
Then why do you have much better data on color ribbons on the left compared to the right? So you see, if you look at the right distribution, I would say your cascade data, like the data is shifted relative to your color condition.
But you don't see the fit here, right? And we see the atmospheric Monte Carlo, you see our data, and you see the cosmic signal has expected from IceCube. Just to give you a hint of how much cosmic signal will contribute to the overall distribution.
Yeah, but you have a total both signal plus backgrounds.
Yeah, so the total is there. What we observe, right?
Yeah, but it would be very helpful to have the total distribution as well, so we see like using color here.
Yeah, I'm not sure the total distribution because of course you have very different efficiencies and effective volume. So the total is not so meaningful in terms of efforts. Right?
It is meaningful because it reflects whether your fit describes the data.
So this account for the for your efficiency or effective volume growth.
Yep.
Um,
The one on the left has pretty good data on the color variance, but on the right it looks a little bit strange. But maybe it's because there's total not plotted on.
so now you're referring to the low energy part.
Yeah.
Okay. So and the agreement with Monte Carlo and like now.
Mhm.
Okay. Yeah. So sure. This is different modelings of the things. So of course it's going to be different reconstruction. So you have different systematics in the different channels.
Yeah.
Yes.
I have a final question. So congratulations on the campaign. I guess what's the time of the campaign?
Timeline. Well, this year you have to go from a conference to another to see the progress list. But if your question is when it's going to be fully deployed, I think I'm going to give you numbers that we probably won't be correct at the next conference, but we are targeting 26. I think we should monitor that on the lower time range. So, in principle, we hope to have at least 24 streams of Orca in January. So this is significant. And we may hope to have a full building block like 2026 for Arc. But depending on the weather changes and the conditions and
I hope it was like.
material supply, etc. So, but the good thing is that we started the templating and the analysis. This can be done along the time, along with the deployment.
Questa è una domanda buona.
Thank you very much for your kind invitation. So I'm going to talk about discoveries in the past decades of neutrino astronomy with Cherenkov neutrino detectors. Before that, let's take a brief moment to just appreciate what we actually have achieved or advanced in the traditional astronomy in the past 400 years. So, this is a drawing from Galileo 400 years ago. He was essentially pointing his telescope upwards and discovered the four horns of Jupiter. And today we have amazing James Webb telescope. And you see, we're no longer just seeing planets and moons, but we're actually looking at the edge of the universe, the beginning of time. Of course, what I'm going to talk about today is a little bit much younger. So this is mathematical astronomy. We're not just looking at gammas anymore, but we're also looking at Z boson, double boson, and associated neutrinos from weak interactions with them. And also there's gravitational waves, of course. If you want to connect neutrinos with photons, it's rather easy. So you can have cosmic rays at a source interacting with radiation field, and it will create charged pions, pi plus, and they will decay to neutrino, and the mu plus will decay with antineutrino. So here the neutrino to antineutrino ratio is not 1:1. And the pi zero will indicate photons, which is a traditional astronomy. And if you have a very strong magnetic field with the synchrotron radiation loss, then this would be prevented, then you will have no antineutrino at all. So if you have another scenario of PP interactions, then you have equal amounts of neutrino and antineutrino. So what I'm here saying is neutrino to antineutrino ratio provides us a completely new different sets of axes to prove what is actually going on there at the source directly. So the confirmed neutrino sources, of course, is a banana. I actually brought the Vector counter on my flight till here, and I can confirm that the radiation from cosmic rays in atmosphere is much greater than what you see actually from banana. We have nuclear plants from Earth, so the nuclear fusion from the sun, and of course, supernova 1987A, the first neutrino source from outside of the galaxy. So neutrinos, they are the window to the extreme universe. This is because high energy photons interact with macro photons with time production, and at the highest energies, we have cosmic rays of which they are charged. And also there's a GZK interaction, which is the cosmic ray interact with CMP photons, where delta resonance. So there is a mean frequency significantly cut short for cosmic rays. So if you want to look at the highest energy, the most extreme part of the universe, neutrinos will be your solution. But it is very difficult to detect them. That's because the cross sections are really small. So we detected Cherenkov radiations from secondary charged particles from the neutrino interaction. So here the leading order interactions are the charged current interactions from declinas scatterings. So you have the neutrino coupling with nucleus, and here is the charged current with double boson, neutral currents where Z boson. And here, if you have Vion, then you have a Vion electron coming out, and you see something like a track. And if you have an electron, then it goes as a cascade. Or if you have all the neutral particles, then you see in the detector as a cascade. So the peak here is a resonance called glass resonance. So it's basically a double boson production on shell. So you have electron interacting with anti-electron neutrino, and this is the hydronic decay of double boson. So it's at precisely 6.3 PeV. And the wave here corresponds to the mass of double boson. And this is also some calculations recently done by Joe et al. So this is a neutrino coupling with photons instead of nucleus. This is about 10% of the effect. So detecting the secondaries, we have Cherenkov radiations, and some of you are very familiar with Cherenkov radiation in the atmosphere. So you have CTA type of detectors to look at air shower, Cherenkov, and you have PLG observatories or HOC that have tanks on the surface with water in the tanks to look at Cherenkov radiation. So what we're doing are the Cherenkov radiation in the ice or in the water, buried deep down beneath the surface. And if you look at neutrino detections, this is a function of energy, and it's also the plot up there. So the up there was from the IceCube original design report about 2000. And you see the higher energy you go, the you need a larger detector mass to detect certain neutrinos. So if you look at the lower energies, about GeV, then we can have underground smaller detectors like super K, so the detector super dense in very good precision, and you go to higher energies, you need about 1 gigaton of mass. So that's what IceCube is doing and ANTARES that section. If you go to the highest energies, then you would need another technique, so for instance, iron tolerance or redo, which Abby is going to talk about later this week. So on the y-axis here is the distance, how far you can probe. So essentially the baseline, neutrino baseline, oscillation baseline that we actually can analyze. And what we're focusing is about here from TeV to tens of PeVs. So at the moment, we have 5 existing and proposed neutrino telescopes. In the center here is IceCube, located at the South Pole. And then if you go to the orange, then this is the ANTARES, PM3 net, going to the Mediterranean Sea. And the blue is P1, very close from here, outflow of Canada. And then this is Trident. So this is a newly proposed experiment in China. And GBD is an experiment in Russia. So let's go one by one. So first, IceCube neutrino observatory. You know, it's at the South Pole, Antarctica. The depth is about 3,000 meters. And we have completed in 2011. So we've been taking data for over 10 years. We have 86 strains and 60 domes per strain. And the uptime is typically 99.7 and 99.9%. It's very function detected. And remarkably, that there are only 36 dome failures since the commissioning of the experiment. So it's extremely stable. So IceCube upgrade is underway. So there's a platform JSON for interesting isolations and fundamental physics. So the sensor we have for IceCube is a dome. So it's the PM2 down up there. And for upgrades, we have new prototypes. And they have been produced or being produced. So this is from DM. 1 PM2 will be up, 1 PM2 will be down. And the end dome is inspired by what Antoine talked about from the Capitolino's design. IceCube Gen 2, so that's a Gen 2 penguin, it's not our logo. So IceCube Gen 2 is essentially a high energy extension of IceCube. So you see the blue points here, so a hexagon IceCube that's operated in the field after IceCube. And then this is the Gen 2 optical, which is an additional 120 additional optical strings, 240 string spacing. So the geometry optimization was done following the Fibonacci sequence. So that's why it's also sunflower geometry. We also have a redo component. Also, obviously, we cover that. So that's going to probe the ultra high energy neutrinos. So this is just an illustration how it looks like. So this is a deep call to probe neutrino oscillations and fundamental physics. The right component is the current IceCube, and the blue is IceCube Gen 2. So I just want to point out we also have as top, so that's the stations on the top because ice doesn't melt. So we could reject the cosmic ray background by putting this surface component, and this is also going to be part of Gen 2. So these are the prototype R&D sensors we're working on right now. So it's a marriage of DI and dome. So you try to put 3-inch PMTs on eclipse with glass. And we're trying to optimize currently the configuration of that sensor. So you have heard ANTARES and PM3 from Antoine. I don't want to go into any of these details. Just want to point out this is a really beautiful piece of human engineering, and it's almost like a piece of art. It's magnificent. For Vico GBD, so it's located in Lake Baikal. So they have successfully deployed 10 clusters and 5 laser stations very recently. So you can see this is a picture on numbers. So they have deployed 10 strings, and the spring points, these are laser stations. So each cluster has 288 domes and depth about 700 meters to 1275 meters. And the goal is by 2026, they will have 1 cubic kilometer GBD with a total of 16 to 18 clusters. By 2026, they will be as big as MQ. So this, you have to be careful. You have to look at this experiments very seriously because they're going to have very interesting data coming up soon. So this is a picture showing the multi-cluster clusters. So if you're in the water, what they usually do is deploy in small clusters. So that means when you have a more high energy events, there will be gaps between the clusters, but you can still use clusters to detect such events. And this is the latest shower data measurement. So you can see there's some axes of raw data, and that's the data on the color ribbons for the backgrounds in pink and signal of atmospheric neutrino in the blue. So they are definitely trying to make more use of their data, and at the moment they are consistent with high-cube diffuse measurement at 3 sigma. So the next one is P1, so located as Pacific Ocean, just offshore of Canada. So they completed 2 pathfinder missions, so STRO 1 and STRO 2, and they measured optical properties of the water, etc. I'm going to cover a little bit later. So very interesting advancement of this experiment is that they have support from professionals, as the Ocean Network Canada, to help them to deploy their strings. So you see that was one of the pictures from the robot arm. So because it's handled by professionals and infrastructure is already there, it saves them a lot of time on planning, and it's very safe that way. So the depth is about 2,600 meters deep, and they have been recently funded, and they will be deploying P11 and the P1 demonstrator by 2027. So this is the design of the matter sensor PMT. It looks also like PM3 net design. And this is the sensitivity of point cells. So the black is where ice cube is. And once you include the P1, it's the gray dashed lines that you see is a significant improvement in sun sky. And if you put all of the neutrino telescopes together, then you get this red line. So there's the ultimate neutrino source of all the telescopes added together. The last but not the least is the experiment on trilings. So this just came to archive a few weeks ago. It's a proposed neutrino in South China Sea. They completed a pathfinder experiment to measure the optical properties of the water. And they have been funded to deploy 3 strings during the pilot project in the before 2026. So the full detector, what the design currently will include more than 1,000 strings and 30 hybridon per string. So hybridon will include both the traditional PMTs and the silicon PMTs. And the depth is 3,475 meters. And they will use underwater robots to deploy and to do maintenance. So you see this is the geometry and this path where the robots will be working around. So of course, with the large area, which is 7.5 cubic kilometers, is compatible to Gen 2, their sensitivity will be increased. It's quite remarkable where they can reach, also because they have very good pointing from water. So why do we need so many neutrino telescopes? One reason is because they all use Earth as a target. So if you want to reject the cosmic ray background, you would want to shield your cosmic rays with the Earth. That means you can't see the full sky. Another reason is because cross section. If you're interested in high energy neutrinos, so this is one of the cross section paper. And you see at TeVPA, almost all the neutrinos from south are absorbed. So if you want to look for the highest energy neutrinos, they can only from the southern sky for ice cube. So this is ice cube cross-section measurement. You see connecting with measurement from accelerators, and this is the prediction for what the radio detectors can do in the future. So yeah, the two reasons. One is ice. One is we want to project background. One is because high neutrinos will be absorbed. So with this all 5 telescopes you see on the map, you'll be able to cover almost the entire sky. So Earth rotates, ice cube is stable here because it's at the pole, for the other experiments to be subjected to the rotation of Earth. But this is basically why we want many neutrino telescopes to cover the entire sky. So the attenuation properties are key to understand how well this different experiment can perform, because the Cherenkov radiation radiates UV photons and optical photons. So every experiment spends a very significant time on calibrations. So for instance, this is P1, so they have dedicated photon emitters, and they have used in the straw measurements to measure the optical properties. And as a Trident, recently they deployed a research vessel, and they have done a similar measurement and ice cube. For each dome, we have a flasher board, and you have these flashers. You can do calibration runs, and this is a particularly special one because this one needs light from different wavelengths. So let me just show the results. This is the optical property as a function of wavelengths. So in water you have very excellent property of scatter, as Antoine said, but the absorption is much worse than in the ice. So if you can't just look at scatter, but you have to see how far the photons can travel. This is why we use this definition of attenuation length, which is 1 over lambda scatter plus 1 over lambda absorption. So then you can compare the water experiments with ice and compare water experiments with water experiments. So these different dots correspond to different water experiments. They are at somehow similar level. And the band here, blue, shows what we have in ice cube. So ice cube has different ice layers. This shows what we have in the deep core region. So you see, in ice, we have very good, exceptional abilities at the UV range, which is where the Cherenkov radiation actually peaked at. So it's important for ice cube, any experiment actually, to explore the photon detection of capability at UV range by using like wavelength shifting material and techniques like that. So if we just compare ice and water using a high level reconstruction, so you see at the left, so this is an ice cube reconstruction of track and cascades. On the right, so this is what Antoine just showed, seawater, tracks and cascades. So all the plots do not have systematic uncertainties. That means there's no systematic uncertainties of ice or water or fish. Here you see actually ice cube has a pretty good pointing compared to ice compared to water. If you don't have systematic uncertainties, the cascade can be pointing at about 2 degrees at highest energies, which is very comparable with what we see currently at ANTARES. Of course, this would change when ANTARES switch to KM3net, so we have more matter sensors, but this is currently what we have. So there are challenges to do experiments in ice and in water. So in ice, because each ice layer corresponds to historical time. So for instance, here, the gas layer, what happened was a volcano eruption on Antarctica. So the photon properties at the stars layer are much worse. So what we have to do is we have to study ice properties at each layer with our calibration device. And we're doing that, and we're understanding ice much better year by year. And this is another issue. So this is a tilt of ice. So it's about 3,000 meters. And close to the rock, the ice are more compressed, and therefore there's a tilt, and this ice is falling some downhill. So on the top we have much more flatter ice, but if you go down, then the ice is not tilted. So this is started with the radar data, and we are in collaboration with many researchers in the Antarctica community. So the challenge in water has been summarized by Antoine. So you have one is bioluminescence animal. So this is the picture was taken by P1 by 1 minute of exposure. And you can see the periods of as a function of time, the rate of this bioluminescence element. The other problem is that the deep sea water is saltier than Antarctica ice. So that means they will have the K40 decay, and they will have this background. And they also have been measuring coincidence rates from multiple PRTs. So yeah, these are the backgrounds, but it seems they're able to control them and model them as correctly in their simulations. So here I want to start with some more results. So in my opinion, the most important result we have achieved in the past decade is we established diffuse neutrino flux from ice cube. So before ice cube fell down, there were no blue points. So in the diffuse universe, we only had the green from Fermi and red from KOG and tensor. And now with ice cube, we actually measured this diffuse flux with different techniques, trapped cascades with different systematics, and we reach a very similar conclusion. It's about 10 to the minus 8 at 100 TeV. So this luminosity density is remarkably similar with what we see in the gamma ray and what we see in cosmic rays. So if you want to connect it to gamma rays, what you could do is simply to extrapolate what do we expect the gamma ray emission will be if at this energy of neutrinos is produced hadronically, and then you can just extrapolate and also take into account the cascaded secondary gamma rays. And then you see that ice cube predicted gamma ray will saturate what we actually observe from Fermi. So that means the sources that produce this 10 to 100 TeV neutrinos have to be dark gamma rays. They have to somehow obscure the gamma rays before they can escape. So this is important because that means when we look for correlations with neutrinos and gamma rays, we probably shouldn't look at the GeV photons, but much lower energy photons. However, this conclusion does not apply if you look at higher than 100 TeV. So 100 TeV and above neutrinos can still be consistent with gamma ray transparent sources. And just want to mention, we have a new result focusing at 3 to 50 TeV from Matteo that he will be reporting parallel session in the parallel session on Wednesday. So diffuse neutrino, we saw that diffuse typical flux plot. So is this a single parallel? So from different ice cube measurements, you can see actually particles not overlapping. Although for each data set, we cannot rule out a single parallel, but we start to see hints. As higher energy we go, the spectrum gets softer. So it is extremely important that we use a global field to unify different detection channels to test the tensions between the results. So there's parallel talk from Eric and Richard discussing how we're doing the global fields next. So if you want to connect diffuse neutrinos with ultra energy cosmic rays, this is a very beautiful model that's led by Matteo et al. So they fitted high energy, ultra energy cosmic ray flux and mass spectrum from Argüelles and predicted how the neutrino would look like if they directly come from such p-value sources. So this is what they fitted. So this would be a component of diffuse neutrino that not associated with ultra energy cosmic ray, and this will be associated with ultra energy cosmic ray, and they seem to be about 10 keV. So that's also what we're working on IceCube right now to expand our high energy neutrinos to higher energy, but of course Gen 2 will be extremely valuable for this measurements to connect with ultra energy cosmic rays. So flavor is something that we're working on. So this is flavor essentially is to measure directly the tau neutrinos, and we have a couple of candidates so far. So I saw this, there could be different tau ratio after neutrino oscillations. They should standard model should all fall in this butterfly. So tomorrow, later actually, Carlos is going to talk about non-standard model constraint with flavor triangle. So at the moment we have a couple of candidates. And we have an upcoming analysis based on a recurrent neural network, and it's very exciting because sensitivity has been improved significantly. So new to new neutrino ratio, we're talking about can constrain the source directly, and this is calculated by the larger resonance. So we published this event. This one is the first candidate, The neutrino reconstructing is in size at 6.3 keV, and we also observed hadronic jets from this hadronic cascade. So we are able to reconstruct the direction of this event, not just from cascade, but also cascade of the track. Okay, so let's quickly move on to point source. So if you want to do point source, you have to make some simple assumptions. So for instance, all the sources are the same in the same category, and all the sources come from the same, contributing to 100% of the neutrino flux. So I'll take this cost with grain of salt. But let's just look at our catalog correlations. So we've done, for instance, recently ultraluminous infrared galaxy, the galaxy clusters where most of the mass concentrated in the universe, gamma ray bursts, also amiga blazars. So this is 7 GeV blazars is going to low energy blazars. We have not seen anything significant, and we've put upper limits for all these classes. And the galactic plane you heard from Antoine. So in particular, this is our new cascade search. This was published for the 7-year cascades, and this was on ScanMap already. So the southern sky basically has been opened recently with the DNA cascade. So this is sensitivity in red compared to the green that previous published version. The green is ANTARES. So you see the sensitivity has been pushed down quite a lot, and also we have the starting track event selection that will be covered by Sarah and also in the parent talk. So the standardized sensitivity is this green. So you see there's no sensitivity in the start, and now we're able to push it to a much lower than we had before. So the first is interesting or the most significant point source in our ScanMap happens to lie just 0.35 degree away from the NGC 168. So the published PRL paper says is 2.9 sigma significance, and now we have improved past 2 data. So please keep an eye on this results. Hopefully will come up soon. So in the end, so I just want to say that we also released our public data 10 years ISQ point source. So everyone is welcome to do to do discoveries for yourself. So yeah, the last one on the list is the real-time alerts. So we have a real-time program. So this is the figure 700922. And you see it was followed up within 57 seconds globally. And, it was discovered there was a flaring laser that was also at time from Fermi, and magically detected more than 100 GeV gamma rays. And the ice cube archival search, we also saw a neutrino flare at about 100-day scale from 2014 to 2050. Okay, so that's the conclusion. We have made breakthrough in the past decade, established diffuse neutrino flux. The question is, are there structures in the spectrum, and if so, why? And tau neutrino and blood resonance neutrino candidates, they open up flavor and give new light measurements and can bring new access to the constraints of source environment. So we have compelling evidence for the neutrino emission from flare laser Texas 0506 to 056. We have hints on steady neutrino productions from NGC 168 and the galactic plane. We have active real-time alert programs across all the neutrino telescopes, and mathematical astronomy is just starting. The future is certainly bright. The new technique and creative engineers go in this field, and I recommend and welcome all the young, talented people to join this field. Yeah, thank you very much.
I'm not sure if I'm the right person, or if you're the right person for this. I noticed the optical properties calibration plots for seawater. So you had all the different, that one. I think people have been doing oceanography for like 100 years. Like, why is that so sparse? Why is this measurement so sparse?
Oh, you're thinking for the x-axis, why this are so sparse?
Yeah, I mean, I think there would be a lot more studies. Are they just, do they have to be incredibly specific to the site of the question?
Sorry, I'm not sure your question is why this is not a continuous measurement.
Yeah.
Okay, so it's because the light source is deployed only has to carry certain wavelengths. It's not a spectrometer.
Is there a way to collaborate with oceanographers to get more detailed data?
I'm not sure, maybe,
Yeah, one.
Of course, it depends on the site. This is what tells you the plot. If you look at the violet points, it seems to have a stronger attenuation than with respect to the orange one.
Are the error bars
Yeah.
smaller than? Yeah, we don't see error
But you're not supposed to see the same measurements on different sites, obviously.
And does it depend on time?
And it does not really depend on time. In principle, it should not so much, no, because it's very large, clean, refurbished medium. So in principle, it does not depend on time. But this can be studied, but it requires more. But yes, if it's site dependent, then you could draw a conclusion from that. In my view.
Any other questions for me? I have one question. So you mentioned a bunch of neutrino telescopes. What, so that have complementary technologies. So what is the, and which one is better for like sources, which one is better for this measurement, the questions of this, you get the design?
so if you look for point sources, what you need is a really good point angular resolution. Probably if you have a water-based experiment, because there's less scattering, in general should have better angular resolution, although we don't see at the moment with ANTARES comparison with ice cream. Yeah, if you look at the track comparison, ice cream can range the flow about 4.25 degree, which is sort of similar with what ANTARES has. Yeah, I think in principle, what it will be better, and I hope this is what they discover in Kouchner. For diffuse, so we need usually cascades of acid because cascade have better energy resolution. So in this case, if you just want kilometric calculation, then the ice is, I think, as compatible. And also because the attenuation, so the absorption in water is much, it's really bad. So if you have high energy photons, high energy neutrinos, I think for collect all the light, probably ice is actually a good choice.
Thank you.
To talk about things like economic estimate, how do we share the interest here? I want to go how those could be a part of it. So let me tell you why I think that I think of very interesting. So there's essentially three reasons that I think that they're not together. First of all, we always see that the neutrino cross section is expressed by if squared, it's for measured quantity. However, this quantity is only small, just a lower measured quantity, which in this case is a standard. So you have size and almost standard interactions. The three interactions are not even. Second, higher neutrinos that we want to today are actually going to propagate on a very large distances. And when neutrinos in a coherent state go over very large distances, they can actually accumulate phases into the interactions that they accumulate in the medium. In fact, we know that the size of long range neutrino interactions led to discovery of transformations. And finally, the just I'm going to talk about today, I'm going to be neutrinos that come from uncharted territories. And those will lead us to unexpected random activity. And so these three are the reasons why I think we should be done. So I want to engage in this adventure by stopping at 4 different stops. So first, I want to talk about the nice set of neutrinos and how high negative neutrinos may actually shed some light on that puzzle, alternative values in a minute. Then I want to think about how to do for that matter with these new finite neutrinos. Then I want to talk about label, and then I want to get some ideas of maybe new ways of doing it. Okay, so we start going by this weekly path. Neutrino oscillations. There are two very outstanding anomalies within neutrino sector. Those are the NSNB and experiments. These two experiments have a mere neutrino beams, one of primary key others and primary gain sources. And they both observe an excess of neutrino-like events on those beams. This excess is beyond statistical level. We know that there is something, sigmas are there. But what we don't know is what this is. And if you think that this is because of conversion from neutrino to neutrino, that actually requires a small difference of 1 electron per square, which is not possible even standard neutrino situations. The thing that makes this fascination interesting is that it's not only those experiments that see something odd. We see something odd through many scales in neutrino selection physics. So here you see in this table, neutrino experiments in the first row, neutrino experiments in the second row, and then you see T-net channels, the T-net channels in community neutrality. Like I mentioned earlier, in the T-net channel, LSND minimum is extremely significant. In the selected neutrinos T-net channel, best is also still significant along the 5 sigma length. Neutrino 4 is less. One thing that's important to note here is that the middle neutrino column here is empty or yellow, which we'll tell you more about this later. But we need to actually see conversion with the channel to see extended neutrino relation. Another thing that's weird is that if you take those experiments as strange things, when you put them as close to the end of the experiment and the distance from the source to the detector, the experiment see weird things and call the hidden effect. And you see that they more or less go along the line. And that's what you would expect from the oscillation experiment. However, there are experiments that are black, it's nothing. That's a so high-end neutrinos are going to go in the direction of the of this question. The difference is that the SQ collaboration, when they observe high neutrinos, as a in the atmosphere, they actually are going to go to large amounts of matter. So unlike the experiments I was mentioning earlier, which provide essentially vacuum, the neutrinos are actually observed and they're going to feed the presence of matter of course the neutrino on the level. And this actually going to have profound implications. What's going to happen is that this matter effect is going to produce a resonance conversion between near neutrinos and the stellar neutrinos. And so the near neutrinos is going to sensitive from the stellar neutrinos for some parameters, for some parameters. What is actually curious is that if the parameters of the amino anomaly, when you put the number C, it turns out that the conversion actually happens over the TeVPA network. This is an accident, but it's an accident. Because at that end of the range is where I skill and then neutrino telescopes are making precision measurements. So how does it work? They're going to have two parameters in this model. You can see on the right, there is the amount of near neutrino in heavy mass state, and the vertical axis is the mass coefficient to light set states. So this equals here show you there is a appearance of neutrinos. Right means that 20% bond, blue means the range. And so if I fix the mass coefficients, and I'm from where I can determine as 2. 1, and increase the mixing angle from small mixing to larger mix, so less near content to larger near content. You see that this is a penis block that's going to move into the core domain. Then I can also fix my amount of near content and then move my mass coefficients from small mass coefficients to large mass coefficients. And what that does, it increases the energy what the setting block happens for the overhead. So this is like an easy problem. Essentially what you want to do, look at your neutrinos, look at the end of the neutrino, look at the rest of the neutrino, and then look for it. That's the game. And from now that game, you get the parameters. So let's do collaboration with that. And this is the latest result, the initial data. And you see here the percentage is in proportion to the near content of the state. Here's the mass reference. The blue dash region is preferred 90%, and it's not below 90%. This is a not significant observation of the 7 However, it's an interesting observation. And the reason that's interesting is because that place where the star is more or less where the other points are also. So when you find something that's interesting, you have to follow that. And that's actually what's going on. So this is last week, my first version Soto. This is a new analysis of the new neutrinos opinions that we proposed that actually uses new machine learning techniques that you alluded earlier in October. And here you can see again the same mixing angle and the mass differences. Red and blue is the traditional analysis, and red is the new analysis which is enhanced personality constructions. And you can see that sensitivity and 99% confidence level increases significantly. So if this signal is there, then the analysis of the receipt. Okay, so now we'll talk about that matter, we're going to go on this direction. We have talked yesterday a lot about how you can look for the matter annihilation from, for example, the center. You can do that also with high-energy neutrinos. To some theory, you can produce stable particles and neutrinos with photons. And then what you can look is for an external galactic center, here shown in the top, high-energy satellite space cube, private from the next one, and this globe squares are more than the. And so you can see from this polar array that there is no excess in that direction. And so you can compare that to an upper limit in the matter annihilation to a unit channel. For example, in this case, it has the minus. But this is not special. You can do it with any of the experiments. Here is a recent compilation. I mean, there are some friends. But we studied how thermal annihilation in the lab is constrained across the board in the experiments. Here's a function of the dark matter mass and the annihilation process in the analysis. There are two interesting things always. One thing is that in the lower energies, we are actually starting to reach level intensity with constraints from inversely measurements. And then the other issue is somewhere around the TeVPA region, let's say some experiments that came today are getting very close to the limits. You can also do this with decay, and I'm not going to go on this because they are allowed to give a talk on this in Thursday. So check that out. There is something that you can do only with high-energy neutrinos, which is the fact that they could interact with the matter. These neutrinos come from faraway places, and so they could interact with something away. So, for example, you have a neutrino matter interaction. When a neutrino comes to the atmosphere, you will interact, and you will have communicating targets more likely to interact. This actually is going to do is going to introduce an isotopic in the sky, we will do for us. This is the hiding in the sky, in spectral events. The color map here is the color intensity, and the stars, and so the crosses and the excesses are the high spectral events. And so, though it looks like there are no events in the galactic center, this distribution is actually an isotropic distribution. So, by looking at the isotropic distribution, you can constraints of interactions. I was telling you earlier about talking about high-energy neutrinos. So, in principle, you could actually resolve the microphysics with the neutrino and the interactions. So, you need to use simplified models to have accessible results. So, here we got the two of these models. For example, this is scalar matter community mediator, or a fermionic matter change. And what's interesting is that these things here will give you different distributions, different distortions of the other distributions. For example, this one has an S-channel process. It gives you a digit, and this expresses the one that of this spectrum. So what we're looking here is not only a deficit of a beta in the galactic center, but that has to be correlated with another distribution. And so you can translate these constraints into constraints on these dynamics here, so the function of the mass, the mediator. And what's shown here is the color scale is very capital of these processes. What's interesting is this magenta line that separates where acid constraints are better, where cosmological constraints are better. This is actually also going to improve by acid collaboration. So the previous result was using high the start elements. Now you can also do medium-sized start elements. So here, for some parameters, I'll show you the survival probability is function of the energy and the angle to the center. And you can see that when you move to lower energies, you actually can get even increased coverage. And so this is a projection of this medium-energy start elements. So I think it's very exciting. So now we talk about flavor. So the typical neutrinos are producing some flavor composition. This is our, let's say, composition of it. We produce it by time decay, neon depth areas where neon radiates and the secondary properties of the two high neutrinos, and then we do that. And so they're going to have some static configuration of the flavors in these scenarios. So when you have a configuration, you can use the oscillations to create a flavor composition out there. So here in the horizontal axis, there you have electron fraction that analyzes the muon fraction in the left axis fraction. So that green globe you see there is when a source is a neutron source, it produces only new neutrinos, and then that size of that region is actually due to the uncertainties of the translation parameters. What's important to note here is that the areas of this triangle is very wide. That means that if you measure the flavor composition that's on the one edge of this triangle, it actually cannot be realized in our physics. This is a kind of mass proof of the physics. This is the ISP-based kind of measurements. And so you see the black line is what's measured. This butterfly in the center is some expectation according to all the oscillation parameters variations. And you see that it's well compatible, but we actually do rule out the rightmost corner and the top corner of the triangles. So then you can constrain physics that will actually be the flavor composition to those regions. So what kind of physics could that be? Well, essentially, anything that distorts the flavor of the neutrino from the source to us could work. You could do, I'm going to go in different variation, but you could think about, for example, neutrino matter interactions that are not flavor trivial. You can think about long range forces. And then when we do this, is we start with a standard oscillation term, and then we have something that is essentially an adult term, that is an operator that's supposed to come from a heaviness to an operator, whose flavor structure is also unknown. I have some scale which we just call it. And so different operator we do different trajectories in this subway life flavor triangle plot. So the white regions is no, the white circles mean that there is no physics, and the dotted circle means that the physics is maximum. So for example, in our line here, you start with an operator that has equal strength in the electron neon, and start with a source that is electron source, and move from the red white dot to the red free dot. And you can do it with different combinations of flavor structures and in certain positions. So we can compare that in the constraints on the emission 6 operator of these interactions, which is like essentially a Fermi-like interaction between anything that's in space and its neutrinos. Here, the corresponding axis is the flavor ratio of the emission sources, and you see muon down finally emitted a little bit on the right. What's interesting is that if space has a non-trivial structure that may be produced by quantum gravity, for example, you think that this operator should start existing at this quantum gravity multi scale, where the size of this interaction or the scale that's for this interaction is comparable to the Planck scale. And what's fun here is that we're seeing that in some combinations of these trajectories, we're actually able to reach Planck scale speed. This is an exciting probe to the portal. It's so phenomenal. Okay, so how do we forward? So this is what we want to figure out. The center is a band of models proposed for new physics. And some of those act on the production of neutrinos, some of them modify the neutrino propagation or neutrino detection. And then those models are going to modify the inner distribution, the arrival of the neutrinos, the field of neutrinos, from that distribution. So we want to measure all of these properties and then figure out which of these models might be in the line. So there are two ways in which we can improve, and this one follows Gustav. I just call new technologies and new techniques. The new technologies. So across the world, we have seen improvement from machinery applications. So for example, we know that, for example, with SP paper, that the angular resolution can be improved significantly based on machine learning and neural networks, simple on the routes. The blue is machine learning, and the gray is standard this. So this is actually something that I think is going to happen in more experiments. And for that, my group is developing this open source, telescope simulations called Prometheus, which allow you to simulate any neutrino telescope you want. For example, here you have a cube, GVD, or TAP, or P1, and you can use that to break the light yield of your different geometries. And hopefully, that will be able to develop more machine learning application. Oops. But I think that's only the appetizer in the use of machine learning in neutrino physics and particle physics in general. You have to think about that in 10 years, we may have to have some degree constant quantum computers. But one thing that I'm thinking about is, well, if you have a quantum computer, how does that help in machine learning approaches? And one thing that's interesting is that you can actually load data in a much more efficient way into a quantum computer and process it to produce algorithms that are more powerful. One of the first things you have to do to solve this problem is you have to take your data and put it into a Python system. And to do that, we have developed an algorithm to encode information in an optimal way by encoding the bits actually in configuration of Python states. So this plot here shows you the evolution of storage as part of time from the old days with files and paper to the 20th century. And now with sort of qubit system that we propose, you can actually store large amount of data very efficiently. For example, Google Drive can store 44 qubits. So hopefully this will help in the future. Okay, the other direction I'm thinking about is new vectors. So Lou was saying earlier that there are a bunch of experiments being proposed over the next generation. As we do, binary DD, internet, and one others. And these different experiments are going to have different capacities that we can start the flavor composition of the neutrinos and the absolutes in general. So I'm going to think how this is going to work out in terms of, for example, trying to measure the flavor ratio of the neutrinos, which I was showing you earlier is part of the physics. So we should think first that there's going to be the S-cube experiment as well as the internet. And one thing that's interesting about the S-cube is that it's an experiment that is expanding in two directions. And one direction is going to have the upgrade, which Jason was getting up yesterday. And then another direction is that has to be 2, which is going to be darker. And this is going to help in different ways. This upgrade is going to help in flavor identification, so improving the flavor function of the signal image. In the other direction, SQB2 is going to help with having various statistics, various sample sizes. Additionally, SQB2 is not only going to have a nice radius, nice optical system, it's also going to have an autonomy array system in the top, as well as radio. And these different technologies are going to help us figure out or measure the different parts of the spectrum. But that's not the only effort. We actually have scheme neutrino detectors. And these are essentially operating by the premise that you have a neutrino, interacts with a mountain, you lose a brain and educate. Depending on the end of your shower, you can detect different signals. The interface is very high energy, you will look for red emission, we will look for the cosmic shower or flight, and whatnot. So your detector here can be scintillators, photons, or else. One thing that's important to note here is that the acceptance of this detector is very dependent on the geometry in the shape. So you will like to have actually a better geometry to present something like this, where most of your showers actually contain in your detector. However, this is not a practical. So one idea that we're thinking about is this idea called tempo, which will have actually a very steep value, but you have essentially one-to-one mountains. Where the three interactions with one side of the mountain and the solar hits the opposite of the mountain. And in that case, your geometry is obvious. And I invite you to look at how a science for looking at the number which we talk broadly about internet development. So this slide is where I'd like to end up. Here is time. And you see here 3 interesting pandas. So the top one is the volume of the neutrino telescope we're going to have. We have right now IceCube, and then we're going to have very soon IceCube, sorry, the and chemical nets. And then later, over the next decade, we'll have more experiments, such as P1 and mono. And so the effective volume of neutrino telescope science is going to increase from 1 to about 16. But that's not only the entire picture. There's another important component to this picture, which is the neutrino properties that we measure in circular experiments. In this middle panel, you see the neutrino oscillation parameters, the mixing angle and the phases, and the phase. And you see how those are actually going to be also improved by Juno, Dune, and the SQL upgrade, as well as all. So the improvement in the oscillation parameters, what that does is it reduces your mix of predicted composition. So for example, this green block that was kind of large right now just becomes the small lighter green and almost on top of the triangle marker. The same happens for the Neutrinos. So now you have very well-defined final decisions. Essentially, your flavor composition becomes set. At the same time, the neutrino telescopes are managed into actually very more precise measurements. So here you see our projections, and so the smallest of these solid blue circles is what we should see in 2040. Hopefully, only because this one here. Well, this is my take home message. I think really be interesting times. There are the new probes are available in all processes in the mail. Certain anomalies can be extended to neutrinos. We'll know more about that shortly with the analysis. I think sufficient neutrinos provide new ways to settle that matter. And flavor of neutrinos is a very indirect probe from new physics of anything that may be contained in space that will modify neutrino propagation. Again, in future, very bright neutron telescope, the new detector technologies. I hope that for your chosen theories, you discover something. Thank you very much.
So we do have time for questions. So let's talk. So when you mentioned the short baseline neutrinos lie in a line, is that telling us physics or is it telling us that we can build neutrino?
Good question. So here I actually only draw the experiment that I'm for anomaly. The all experiments that are not here or the
But those exist.
Those exist.
Okay, it's not just.
It's just that these are experiments that actually prove this particular physics, but they're experiments on the top on the right.
The selection method.
Yeah.
Good. Do we have other questions? There was one there.
I can shout if you can hear me.
Well, let's try.
Yeah, I just wanted to ask about, you were saying that you can provide external neutrinos with IceCube. Is that mainly like what mass range, and also is that more with high energy astrophysical neutrinos or with atmospheric neutrinos to oscillations?
Yes, that's a really good question. There are actually two ways in which we can measure atmospheric and neutrinos in these detectors. At below 100 GeV, the oscillations are averaged out, and you can see modifications to the oscillation parameters. So that's been done by ANTARES and the core, as the course. A higher value in the TV neutrinos usually is a resonance conversion feature. And so essentially, between say 0.1 and somewhere around 2 or 3 electron volts, the resonance happens in the regime where you're still in the tens of TeV in the range. Once you start going above like 5 or so electron per square, this resonance actually moves into the region where a statistical component is significant, like 10 to 20%. So one thing that we did to increase the sensitivity of this analysis from the blue to the red is to actually increase the threshold of the analysis from only like 20 TVs to 100 TVs, which adds a statistical component more linear self-interest.
Thank you.
Okay. Last question will be.
Thanks, Carlos. Just a question of the timeline in your slide 44. I noticed that the Juno, according to your slide, is supposed to start very soon, like at the end of this year.
Yeah, I think the Juno camera, I'm not sure today. Okay, well, so our timeline was written a couple of years ago, so please do appreciate that. But I think the Juno is far away from that. You know, maybe 1 or 2 years to delay, but I don't recall exactly how that's in the range. This time that we got a couple of years ago, so maybe it's a different.
And the delta value for this plot, do you know? Is it about?
Yeah.
Thank you. So let's thank Carlos and Giovanni. Our second speaker is Matteo Cerruti. Will tell us about energy neutrino Blazars, I believe.
Okay, can you hear me? Fine? Is it okay?
Is it on?
Is it on? Wow. That's not- Yep. No. No. I guess I don't. Yeah, that sounds good. Okay, hi everybody, I'm Matteo Cerruti. I will talk to you a bit about Neutrinos from Blazars. So first of all, thanks the organizer for inviting me, and thanks for preparing a morning session, which is actually allowing me to move towards the astrophysics part. So I work with HN, I'm an engineer, I work with the Cherenkov community, I work on neutrinos themselves. But I will be trying to understand how can we actually learn something from multi-messenger observation of neutrinos and photons from this evidence. So as you probably know, I assume that you are familiar with the fact that right now, 5 years ago, we got the first evidence of joint neutrino and photon emission from a source, which is the data Texas 506. I'll try to show you what did we learn from it and what happened in the last 5 years. So this is what happened, well, 4 years ago. So the event happened on September 2017, the publication around something like 1 year later. And for the first time at the 3 sigma level, we have the first evidence that a neutrino detected by IceCave was actually coming from a direction consistent with the known photon source, which is a laser. Texas 506 plus 056, and it is shown here in the city, but it's detected in gamma rays mode at the GV band and at the TD band by Fermi and Finch. So first of all, let me try to recap for everybody who's not working in the field. What are we talking about? So what are we talking about are supermassive black holes. So we now know that basically in every galaxy we have a supermassive black hole. We have seen the picture that now we can take of supermassive black holes. And we know that in some cases, the accretion onto the supermassive black hole is associated with an outflow. So we see this thing flowing away this kind of jet of plasma on the polar axis. We call this radial loud AGN. And well, whatever. And in some cases, just for chance association, one of the jet points towards us. So that's what the blazar is. We are looking down in the jet of a supermassive black hole. We are completely blinded by this radiative emission from the jet, which is Doppler boosted to stars. From an astronomical perspective, there are two populations of lasers, but we don't really need to care about it. We talk about FSRQ, flat spectrum radio quasars, and the LHRT objects. So this, if you plot like the photon you collect as a function of the frequency, that's how it looks like at lasers. So this is a spectral energy distribution. It's a very famous plot from more than 5 years ago. You have how much luminosity they emit as a function of frequency, and all blazars are characterized by this double band structure. So they look all the same, and these two bands move around. So they move around in the population. We see blazars which are bright and the first peak in the infrared. And we see blazars with the first peak in the X-rays. And this SCD moves around also in the source. So we see sources which are flaring and varying with the peak move here and there. So when you heard about LDL and HDL, you heard about subclasses of the world laser. So what we're trying to do is, of course, trying to understand how these photons are produced. We have first what we call the tonic models, which we assume that what we are seeing here is actually emission from a plasmoid in the jet. The radiative mechanisms are very well known, are synchrotron radiation, and so we know that what we see at low energy is synchrotron radiation by population of electrons in the jet. And in the tonic models, we know that what we see at high energies is actually inverse complex scattering. Then again, the details are very complicated. We can discuss its inverse complex scattering of what on what. but we don't care. So it is just, you have a soft photon field that is somehow abstracted to high energies, and that's what's producing the chemicals. Then the hadronic models came, as you can see from the very first hadronic model paper for Blazars and in the 90s, really. And the idea is, okay, what happens if we put protons in the jet? And so why do we want to put protons in the jet? Is that because then we have a natural link with cosmic rays. So if you can show that actually energy and jets, you have a population of relativistic protons that can get the link, and you're actually trying to identify the sources of cosmic in the universe. So the first thing that happens if you put protons in the jet is that the synchrotron radiate as the electrons do. And so interestingly, you can have this kind of proton synchrotron model in which your two bumps are naturally explained as an electron synchrotron emission and a proton synchrotron. The problem is that, as you have seen, whenever you put relativistic protons, they interact. So you cannot just have them and radiate as proton synchrotron. They do proton photon and proton proton. So in Blazars, the dominant channel is proton photon. The density is very low. Usually, I mean, you can have proton photon interactions, but usually the dominant one is the gamma. And then in the gamma, you have the photon vessel production and the beta production. And so the modeling is complicated by the fact that you need to take into account exactly how these cascades are producing energy. So this electronic versus hadronic problem is typical, and basically in every Blazar paper, we always try to discuss if what we are seeing is consistent with electronic emission or hadronic emission. Here again is a very famous paper because it was the first paper that included the Fermi-like data on the particle study in Blazar, one. And then you can see that the SCD you cannot really distinguish. I also point out that, as you can see, the hadronic model is usually very complicated by the fact that you have several components, one on top of each other. So you have proton synchrotron, muon synchrotron, cascade emissions. So in 2017, technical 506 happened. Here I show you some things that we learned from this thing. As surprising as it might seem, from a single event at 3 sigma, we learned a lot. So we could, for the first time, put constraints on the electronic versus hadronic thing and discussion, because we could actually test models that were predicting a neutrino flux coming from the pion. So the first important result that we achieved is that we can exclude, at least from the source, the whole proton synchrotron scenario, because in the proton synchrotron scenario, we have a very low neutrino rate, which is expected. So there is no way you can get the neutrino that IceCube got out of it. The solution that we put forward is actually something in between that we like to call it mixed or hadronic solution. So here, what you have is the SCD of flexible 526. These are the neutrinos here, and then here you have the bulk of the emission is actually electronic. It's inverse compound scattering, SSC, and then everything that happens here, which is subdominant, is the hadronic cascade contribution. So here at low energies, you have data pairs, and at high energies, you have pairs from biophysics. And this works fine. Several loops got neutrino rates in the order of 4.1. Which are consistent with the one event that we put. There is one important caveat for hadronic models, and it's energetics. So P-gamma interactions are not very efficient, and so basically what you need is that you have your photon flux, neutrino flux, and to get the source, I mean, that amount of photons or neutrinos, you need a lot of protons. So the question is, okay, you can compute how much energy you have in the proton, and of course you cannot exceed the energy that you injected at the beginning in your engine. And so we have one way to estimate how much energy is available at the center, and it is the energy luminosity. Of course, it's a benchmark with just an order of magnitude estimate of how much we can, how much this supermassive black hole can actually accrete and then launch in the jet. But if you have models that require a very super random temperature region, then this is probable. So of course, this is for what we call the one zone emission models. You can reduce this problem if you increase your gamma. So we have big gamma interactions. You can lower the P if you increase the gamma. And so there are a lot of work that have been published on Texas 506 showing that if you have a very bright external photon field, you can have efficient big gamma interaction without issues in terms of energy luminosity. And then the question doesn't become what are we doing with direction onto? We can actually a few examples. This is on a generic body, or you can have more detailed modeling either of the jet. So this is a two structural jet and the jet layer photos, or on a radiating inefficient accretion flows. Another thing that you are aware of is that once we got this 2 sigma optimal center evidence, that's the collaboration looked back at the data set and found evidence of 3.5 sigma of the neutrino only flare in 2015. And I would say that this is even more interesting because it is very constraining for our clients. Of course, at the time that we were no alerts, so the amount of equipment data we have is very limited. But we have survey instruments such as Fermilab, we have some limit in X-rays, and we have some observations in optical. And you can see that basically all the models are failing to reproduce the SCD. So this is the spectrum of high speed that you get in this treatment facet sense. And you can see it's very difficult to have it consistent with the photon emission. And the reason is because in the photon emission channel, you have as many neutrinos as air to inject in from the planet decay. And so these pairs need to radiate somehow. It's very difficult to let them not to radiate. So we have two ways out. The first one is that you put all your power for the cascade in the MEV band, which is the one on which we have the list of sufficient constraint. And you can do that for some part of the parameter space. And the other way is that you find a way for your pairs to just escape the neutron region and not radiate anymore. And so you can have this kind of decoupling of the gamma and the neutron region. So what happened since then? So what happened since 2017? We kept going because it was a very promising path, and we have several new events that got associated with some at some confidence level with some lasers. So the first one is 1907-30. It was associated with parts 1502 plus 106. It is an FSRQ for radio distance, 1.8 and redshift. And there is a spatial association, but not flaring activity with the neutron event. So here you can see the Fermilab light code. The neutrino right here, you can see that basically right at the minimum of the Fermilab emission. Another element which is of interest is this extreme laser, 3 HSP J0915, again, rather distant, 0.56. I would say that the situation is very similar. We have spatial association, so the probabilities are around 2%, but there is no flaring activity. The source was doing. Here you can see a comparison between archival data and what was going on during 2019. And you can see that there's not really flaring activity. Maybe there's some kind of hardening in the GD band, but it's not this. And I think the interesting thing is that if then you put this together, so you compare your X55 in right with the two other sources, you can see that there are three very different beasts. And I don't know, personally, to me, it's a bit strange that you're seeing association with very different kind of objects within the whole piece. The other thing I would like to mention is something which is still preliminary. In 2021, December 8th, there was a new alert by the ASCII collaboration. There is a last source which is slightly beyond the 93% return, and it is a laser, Blazars 0735 by 17. The redshift is unknown, although we have a solid lower limit of 0.4. And the interesting thing is that basically all other neutrino telescopes sent ATOL claiming at some confidence level 11%. Also the data set and by Cal came into the edge and plus. The interesting thing is that if you now look at the flaring activity, so that as light curves, the source is flaring a lot. So this is the only, as far as I know, paper coming from theories on this source. And you can see here the Fermilab light curve, the X-ray light curve, and the optical light curve. And you can see that the flare is very bright at all wavelengths, and it's very short, and it's very coincident with the neutrino. Interestingly, here, you can see that now if you superimpose the two sources on the spectral energy distribution. This guy is a cousin of Texas 506. I think it's very difficult to decide who is who if you don't look at the agenda. You can see in you have Texas 506, the low state and the flaring state, and then in yellow and pink you have Parks 725 in low state and the flaring state. You see that very so coming back to what I was telling you before, so this is what we call the Blazars sequence. So a sample of a typical Blazar recipe, and you here you have the same, just it's plotted with inverted axis. So we have the frequency with the peak as a function of the luminosity, and on the other way around. So you can see the Texas 506 and thus 0735 as well stands out as a kind of an outlier within the Blazar population. So we are observing that somehow the brightest and high frequency peak sources as what's called neutrino mountains. Other works that happened in the last years. First, I will show you the neutrino only thing. So this is the paper by Gasper collaboration studying evidences for candidate evidence signal from Blazars. Then you can see that there are some hotspots. Again, these are at 3 trial significance at most. We are at 3 sigma from MH7. Texas 506 pops out as well. But post trial, of course, nothing is really extremely significant. And then on the photon only part, we kept observing Texas 506, 2056. So before the 2017 event, Texas 506, it was a very poorly studied object. We didn't even know its redshift. It is true that it was particularly difficult to estimate things like the duty cycle of the source if we didn't model the source. So we had firm, of course, but in other ways, it was much tougher. So here it is a paper by the Magic collaboration that came out 2 months ago, and it had basically everything after the neutrino alert. So you have the neutrino, which is here, and then we got data up to early 2019. There were 2 things I would like to highlight. The first is that we got new very high energy flare in 2019. You see at the top subplot there. This behavior of the source in the GB band was very different compared to 2017. We don't have this kind of a long-term high state that was happening there. The source went down to a much lower baseline flux, but with very rapid flare, much shorter on time scale of weeks. Interestingly enough, the radio goes its own way. So you can see that's completely uncorrelated to anything else. We have a long-term ride that is since 2017 in trade band, and it will keep awesome. So now let me go to the second part of the talk. Here I will, so until now I'll show you what's going on in terms of multi-messenger correlations on single event. But of course, as was previously discussed, we can also try to understand what are the sources of neutrinos by looking at those searches and study analysis. So first, let me show you the 2 most recent papers by IceCube and ANTARES on the all-sky searches. For IceCube, the hottest spot is at roughly 3 sigma post trial, and you can see that 16, as I discussed before. And Texas 506 still stands out at the second or third most significant hotspot. And from the ANTARES 20-year paper, we also had hottest spot is taken incident to the Blazar for minute 1, 2255, which interestingly also had one of the IceCube neutrino events coming from interaction coincident with it. And so if you put the 2 significances together, that's something again around this. Then I quickly mentioned this paper that was already mentioned before. So this is one of the first IceCube paper trying to put in constraint of the contribution of Blazars to the diffuse neutrino flux. And as you can see, so the 2 bands are limited to 2 different indexes. The conclusion is that Blazars cannot contribute to more than 20% of the diffuse with 2 important assumptions. The first one is on the spectrum. So with this range of spectral indexes, and then assuming that basically all fermionic Blazars behave in the same way, and you don't have a subpopulation contributing in different way or at different energies. Let me mention this paper. This was published in 2020 by Clavin and collaborators. There were other papers, other follow-up papers after that. So this is a study which tried to estimate the probability of a correlation between ice-filled neutrinos and regular AGN. So this is a broader study in terms of AGN mechanics, which is the last one. And you can see that what they claim is that there is a chance probability at less than 1% that the neutrinos are coming preferentially from directions consistent with the brightest among the regular AGN. So I remember you regular AGN, AGN with jet. So it's amazing. You can see that 0506 is also there. Keep in mind, I'm not part of this work. Keep in mind that it was also not confirmed by any authors, nor by ISQ. Yesterday there was a talk, the parliament talk by Valva, and they are trying to reproduce the results that are not confirmed, or they did not confirm at the same confidence level. That's maybe not spot, but it's not at the 11.2%. And then let me continue these two other studies. This is a paper that came out a few years ago by Giovanni and collaborators in 2016. So they tried again to do some correlation study between the whole neutrino from IceCube, and this time not the whole laser population, but try to study if there is any preference for specific laser subclasses. And they claim at the 1% that there is some evidence that H-cube lasers are actually contributing to the diffuse. And then a paper that came out 3 weeks ago, it's very recent, very fresh. I still didn't have time to digest it fully, by Salaguzon and collaborators, claiming, I think, what it is the lowest chance probability or the highest significance of a correlation between ice-filled neutrinos and lasers. This time we are using the basic cut, so it's basically the largest or a collection of laser catalysts from multi-wavelength information. So it's not just turbulent lasers. And you can see here we have the chance probability as a function of radius of the association, and in the lowest one they had there to the log to the minus 7. So to conclude, what happened in September 2017 is still the best thing we have in hands, and it's still the best evidence for this multi-messenger emission. I'd like to apply it every time that we learned a lot from this single event of 3 sigma, and it is really, it does a lot of try to understand how the laser work or might work, and how can we constrain actually the particle contained our particles and go to this. We have had several new multi-messenger campaigns, of course. The path I think is fake. We are seeing the hotspot here. We didn't have anything new. Keep in mind that we should wait and see what's going on 735. And once we have all the neutrino information from all the neutrino telescope together, and the probability of the association with this flaring in the multi-wavelength emission, and how significant it could be. In terms of whole-space searches, there have been several claims for significant association. Nothing formally from the IceCube collaboration, but several groups are claiming that at some hotspot level, we have some evidence that lasers are contributing at least in part to the IceCube neutrinos with this basically 5 sigma detection claim fields. I would always like to end with some questions. The first thing we would like to ask is that are we actually learning something on AGNs by this somehow conflicting claims on using different data sets? Maybe we might have indeed hadronic lasers and electronic lasers, and these dichotomy might not overlap exactly with what we had before. So maybe we should not be biased too much about what we already know of lasers. Maybe neutrino lasers are different. So where do we go from here? I think the other thing we learned in terms of observations is that RH rays and very energy gamma rays are critical to constrain the models, because that's where the hadronic component emerges. We have beta ion coming out in the X-rays, and we have the photometal coming out in the TV band. It is clear, I think it's not just for us, but in general astronomy, that we are not whole in our coverage of the universe. So there's a huge need for every satellite, and we are, of course, waiting for the next event or not, because any time that passes without any clear association, of course, we are constraining the models more and more. And at some point, if we don't see anything, guys, that's also a very useful information for us. Thank you very much.
Time for questions. Yes.
I understand correctly that the predictions of the hadronic models based on the homogeneous time independent scenarios.
Oh, well, you have several of them. Here I'm showing you. So let me go back to the test of 506.
What will be the predictions of Neutrino fluxes in the case of time independent models? Do you think will be
Okay.
lower or higher?
Okay, so here you have, I think, for example, here it depends on the code. So it is true that here I always show spectral energy distributions. Many of the codes here are time dependent, so they actually can predict light curves. And for example, here for this 1502, they actually can reconstruct how the flux varies as a function of time. I think the reason why we don't, or very few people right now predict light curves of Blazars is that we have one neutrino event. So it's very difficult. I mean, we can produce light curve in neutrino and try to estimate when we will have the maximum and how it correlates with gamma rays, but we cannot constrain anything yet because with one event it's possible to do anything.
So concerning models for the excess for the emission of neutrinos, what about the models claiming that you can produce neutrinos inside the core, inside the application? Would they be compatible with the flare?
Oh, okay, I see. I would say yes in general. So we have models right now. Again, I didn't mention it explicitly. So in which the emission is not produced at the jet level, but it's produced at the core of the AGN, so very close to the black hole. I think they are in general all models which predict a neutrino emitting region which is opaque to gamma rays are of interest, especially for the 2014-15. So in which you need somehow to suppress your gamma ray emission, and so you have like the Blazar emitting region, which is far from the disk, from the disk and the black hole, which is producing the bulk of your photon emission, and then you have the neutrino emission. These are they're starting to get a study for this flare, for Argüelles-Delgado 68 as well, which is very constrained if you measure upper.
Other questions? We not then let's thank a few again. Our third speaker is Giovanni Morlino on select clusters party acquisition and emission.
Yes. Can you hear me? Okay. Thank you very much to the organizer for the invitation. It's a pleasure to be here in this beautiful environment. So let's change topic. We move now back to the galaxy and back to gamma rays. So I will talk about today about the possibility of young stellar clusters to be interesting contributors to produce cosmic ray galactic. Okay, so when one wants to explain the cosmic ray spectrum we observe here, there are a few questions that needed to be answered. The first one is the energetics. So in order to explain the bulk of cosmic rays, you need an energetic of power roughly 24 hours per second, which is really concentrated at 1 GeV level. Okay, the most of the power is there. The second issue is the spectrum. that is up to the knee, roughly E to minus 2.7, that requires, once you convolve for the propagation in the galaxy, requires an injection spectrum which is close to E to minus 2.3. The third thing is the maximum energy, which for protons have to be up to the mean, so 10 to 15 electron volts. But this is the minimum level actually, because if you look now at the spectrum covering from the knee level up to the envelope, and you assume that you accelerate protons up here, you can explain the second knee as the pump, the maximum energy of ions. But then they have more than one order of magnitude to cover from the second knee up to the end. So either this region, if the maximum energy you have just a cutoff, either you fill this region invoking some kind of extra galactic sources, then you have two different components, one for the end, one for this region, or you should have the galactic sources also covering that region. So this would imply that you need to accelerate particle up to energy way above the need. The other information is the anisotropy. Anisotropy is a quite small amount. This is the amplitude that is phase, and the amplitude is small, 10 to minus 3 at 10 GeV level. That means that you need several sources. It's not enough to have one single source close by to produce PV particle in order to explain what you observe. We need several. Now, the exact number depends on the diffusion coefficient, especially on the diffusion around the source. And the final requirement is the composition that is more or less very similar to the solar one with few exceptions. The most relevant one is the fraction of nu24 over nu20, which is roughly 5 times larger than in the solar system in cosmic rays. So your solar should be able to produce this excess. Okay, for many years, for decades, supernova remnant have been considered the most promising candidate for the production of cosmic rays, and the reason is mainly summarized here. First of all, there is enough power. It's enough that supernova inject 1% of their energy into accelerated particle to explain the cosmic ray flux. There are enough sources to explain the anisotropy level. We have a theoretical framework where we can explain the particle acceleration, which is ESA, if this is shock acceleration. And also we are sure that there are accelerated particles inside the remnant, because we see, especially the electrons from those reports. On the other hand, there is a main inconvenience. There is no clear evidence that supernova remnant can accelerate particles beyond 100 TeV. And also from a theoretical perspective, we are not able to explain this. I will show you in more detail that only very rare and powerful supernova remnant can indeed accelerate up to the TeV. There are also other minor issues like the neon 24 neon 20, so anomalous composition, which is difficult to explain in framework of supernova remnant. There are also some spectral anomalies. For example, the fact that hydrogen, helium, and CNO, they have different spectra. But those are sort of minor issues. The main issue is maximum energy. And let me explain a little bit more in detail. So when it supernova expand, the velocity goes like T to minus 3.7 during the ejecta dominated phase, and then it decreases faster. Okay, T to minus 3.05. This means that the radius expand quite rapidly at the beginning, but then the rate of the expansion decreases. Now, if you are accelerating particles diffusively, like the SIG, particles ahead of the shock, they propagate diffusively. So the distance from the particle ahead of and the shock layer goes like the square root of the time. This means that during the ejecta dominated phase, the shock can catch up particles continuously. But after that, particles move faster, so they just escape. The highest energy particle cannot be catched back by the shock. And so this means that the time that you are available to accelerate, to increase the maximum energy, is just the ejecta dominated phase era. So if you now make this assumption that your maximum energy is given by the acceleration time equal to the set of Taylor time, what you get that is an expression for the maximum energy will depend quite weakly on ambient parameters like the ejecta mass, the explosion of the remnant, and the density of the environment. The only parameter that you can actually tune is the turbulent magnetic field, is quantity here, which is essentially given by the turbulent magnetic field over the regular one to the square. Now, in order to get EV energy, you need this value to be much larger than 1. This is the reason why we have been invoking the magnetic field amplification since forever. Not forever, since when we realized that if you implement the magnetic turbulence in the average galactic magnetic field, what you get is a maximum energy that is at the level of few GeV, at most 10 GeV. So you need to accelerate the magnetic field. We're really scheming or proposing the resonance filling instability that being most important for years. But this instability can give you turbulence, which is at most close to 1, but in general smaller. There are other MHD kind of instabilities that at most they can give you an amplification up to 1. So turbulence, which is close to the average magnetic field. The most relevant one that we have been discovered in the last 2004 by Bell is the called the non-resonance streaming instability. This is the only one that can allow you to go beyond the level of 1. So the turbulence, which is growing much than the average magnetic field. And so this can allow you to reach PV vacuums. But now, if you implement this scheme of particle acceleration, you can calculate maximum energy for different kinds of supernova, for type for total supernova here, and for type 1A here. This is essentially the maximum energy as a function of time from the explosion. And you see that for type for total supernova, you can actually reach PV, but only in a very short time, within tens of years from the explosion. For type 1A, there's no gain. This is due to the fact that the saturation level of the magnetic field is a function of the density of the upstream times the velocity of the shock. And the type 2 supernova are expanding inside the wind of the progenitor. So it is an environment which is denser than the typical interstellar medium where type 1A are expanding. Now, take the result from this calculation, and now you want to answer the question, what if I evolve the remnant for the entire life and then take those particles, propagate through the galaxy, and get and compare the result with the cosmic perspective that we had at the Earth? This is an exercise that has been done in this paper, for example, by Stefano Matteo, accounting for 3 different types of supernovae, type 1A, type 2, and what they call type 2 star, which are very powerful supernova remnants that have expelled almost all their material through a wind, so there is a very dense environment around, and the ejecta that is related to the explosion is very small, it's order 1 solar mass. This guarantees you to have a very dense environment and at the same time a very high shock speed, just because the ejecta mass is small. Okay, let's see what happens for type 1A. This is the result. The solid line is the total cosmic spectrum that you predict, which is composed by one component, which is the particles that are stored inside the remnant and are released when the remnant die. And this is instead the flux of particles that are continuously escaping from the remnant while the remnant is still accelerating. You see that the spectrum does not give the data at all. The maximum energy that you can reach is indeed of the order of several tens of TeV, but you get this thickening, which is due to the evolution of the remnant. The same game for type 2 supernova is even worse, because due to the peculiarity of the environment, even if in principle you can reach PV particles, but the amount of those particles are very few. So it's small, and so you get this shape which is quite steep above few TeV. Okay, so the things are better for type 2 star supernova. Here, those are more powerful, and so they can accelerate even beyond the PV. Now, don't matter about this band because in any case, if you integrate over several fragments, maybe this just disappears. But the point here is another one. Assuming that this is actually those type of remnant are responsible for PV particles, they should also produce lower energy particles. And so at this point, there is no room anymore for the other remnant that we see, that we know, and we can estimate the amount of particles that are producing it. So this is it's difficult to put in the framework of supernova scenario. Also, if those are penetrons, the only penetrons, the chance to get to one of those objects is very rare, because this is the rate that you would expect from this kind of object. Okay, so this just to settle the ground. Now, what about winds from why they're so this is a typical scheme of a remnant, a spherical geometry where you have starting from the outside or inside, the forward shock, the contact is continuity, the reverse shock, which is expanding inside, so it's compressing the interior of the remnant. If you compare this scheme with the wind from a star, the geometry is the same, but things are a little bit different. Here you have continuous injection of material from the interior, so the wind is expanding, producing a termination shock. So here the reverse shock, we call it the termination shock, and I'll lose here. And then there is also contact discontinuity and the forward shock here. So the geometry is similar, but if you go to evaluate the velocity of the shock for the forward shock of a supernova remnant, this is very fast, while the reverse shock, well, it's smaller, but still with the relevant velocity. Concerning the forward shock of the wind blown bubble system, the forward shock is totally unable to accelerate particles because the speed is barely supersonic, so completely irrelevant. Here, what is important is the reverse shock, so the inner termination shock. That is more powerful. The velocity is of the order of 2,000–3,000 kilometers per second, and also the age of the system is different. While a supernova can at most accelerate for 1,000 years, wind system like this one, they can last for several megayears, okay, until the star explodes as a supernova. And so this means that the maximum energy will not be any more constrained by the time at this position, but it will be constrained by the size of the system. And the size also is interesting because the size of the bubble is much larger than the size of the supernova, and while the supernova can reach when it reaches, we talked about, can reach 1 parsec, the size of the bubble can be as large as 100 parsecs. Okay, so there is another peculiar difference. While the supernova is accelerating particles that are located upstream of the shock, so the circumstellar medium, the wind system is accelerating particles coming from the wind material. And this has an impact on the chemical composition, especially on the neon-22, because usually winds from massive stars are enriched of neon-22. So in principle, you can solve the issue of the abundance of neon-22. And the other thing is that is related to the magnetic field. The difference here is that the magnetic field, in order to accelerate particles at supernova, you need to amplify, and the only way is through self-generated magnetic field through cosmic rays. On the other side, instead, this does not work, but you can have magnetic field amplified by NHD processes occurring inside the wind. Usually, the wind is not uniform, so you have non-uniform winds that automatically reduce vorticity, and you can eventually produce NHD instead. Okay, let's estimate the maximum energy using the Ilias criterion. So it's very zero order estimate. We know essentially the magnetic field, the velocity of the shock, and the size of the bubble in supernova. So we can estimate the maximum energy. It's already shown for the supernova remnant, you most reach 100 TeV. Concerning the wind, if you take just a single star, single powerful star, because the mass loss rate is of the order of 10⁻⁶ solar mass per year, at the end, you will end up with a maximum energy which is still small, of the order of 10 TeV. But if you now put a lot of stars in a very close space, so you take a cluster, you can increase the amount of wind material that is expelled, and so you can produce a bubble which is much larger. and energy in kinetic energy in turbulence, which is also much larger. And so you can produce a much larger magnetic field, a larger size of the bubble, and you can end up with a maximum energy even beyond the EG. This is a first order calculation. Let's go beyond and making things more reliable. Now we are using a model for the solution of diffusive shock acceleration in spherical geometry. This gives you, is an analytical model. This gives you the distribution function of accelerated particles at the termination shock. And the equation is this one. Is composed by a piece, which is just a power law in momentum, like the plane parallel shocks in supernova island. But then you have two other pieces. So one is a cutoff. It's not an exponential cutoff. It's something. It's a complicated function, but it's a cutoff due to the confinement of particle in a spherical region. So this is due to the upstream, to the inner sides of the system. And then there is another exponential cutoff due to the fact that particles can escape from the downstream, so from the border of the bubble. And those two functions are strongly dependent on the magnetic field inside the system, so essentially on the diffusion inside the system. And here, I'm making this as an exercise that is assuming typical parameters for a massive stellar cluster, and changing the diffusion coefficient, assuming either Bohm, Kolmogorov, or Kraiger. And you see that the final result for the particle spectrum here is multiplied by PQL. So essentially, you're just looking at the cutoff shape. You see that if you have a Bohm diffusion, you can go even beyond the PV energy. But if it's not Bohm, the cutoff is much broader. And so you actually have something which is not anymore power. Okay. So PV energy can be reached, but it's strongly dependent on the type of diffusion, the most favorable being the high. There is another issue. The story I'm telling you is especially suitable for very compact clusters. So meaning that a cluster that has massive stars all close by, so within a radius of, let's say, 1 to 2 parsecs. On the other hand, you can also have loose clusters, so where stars are widespread. And in that case, you do not form a large-scale termination shock, which in this plot of this simulation is this one. And so, why in this system you can accelerate particle using the wind termination shock. In the other one, you don't because there is none. But you still can imagine to accelerate particle by wind termination shock from single stars and by the process of wind collision. The point is that in the other case, at the moment, there is no realistic theory describing particle acceleration in such an environment, while for the first case, that's the Okay, here is an energetic problem. If you were to explain the entire cosmic ray spectrum using only young stellar clusters, it is not that easy. The point is that stellar wind are radiation driven, so the momentum of the wind is essentially proportional to the cube of the mass of the star. And so the final power of the wind, given that the velocity of the wind is more or less proportional to the escape speed from the star, and so the final power will be proportional to the m to the 4th. This means that only very powerful stars are important. And for those stars, if you make the calculation, the integrated power of the wind is more or less comparable to the energy of a supernova explosion. And now, if you take an entire calculation of stars, this means that while stellar winds are important only in the tail of this distribution, supernova can contribute above roughly 8 solar mass, and mainly above the mass where stars explode as supernova. So at the end, if you make a calculation, supernova in terms of power may win by a factor of 10, even though one has also to include the fact that above some math, we know that exists the so-called failed supernova. Essentially, those are stars that live, but when they go to the end of their life, they collapse directly to black hole without forming a supernova. This means that the entire power provided by the stars is only through the wind and not through supernova. We are not completely sure about which is the fraction of the stars that ends in this way. So this is an open issue. So stellar winds in general, we can say that they can be subphenomenal. but in principle, they can dominate the flux at the maximum energy at PV level. Okay, this is not the end of the story. It says that those are just young stellar clusters, but after a while, the stars inside the cluster start exploding, and they form a system which is different. It's not anymore dominated by the wind, but it's dominated by the explosion of supernova. We call those kind of systems superbubble. So essentially, those are older stellar clusters. The typical age where stars start exploding is few megayears, typically few megayears, very massive stars. And so in this system, you can also include the acceleration due to superposition of stellar supernova remnant. And so that kind of system can be energetic to produce essentially the entire cosmic ray population, just because the majority of supernova occur inside this kind of system. You see that this is a plot done by people showing the power of the material inside the bubble, which at the beginning is dominated by the wind and then is dominated by supernova. In this paper, they made the exercise of considering particles accelerated both at the wind termination shock and the forward shock of supernova, and also due to the turbulence which is enhanced in the region. So essentially, they have three different forms of particle acceleration. And in the final result will strongly depend on the number of stars that massive stars that you have in the new cluster. And here you see that the energy density of cosmic rays as a function of time, and for different cases of different number of stars. And if the number of stars is quite small, you see a strong fluctuation just because this reflects the explosion of the stars. If the number of stars is larger, the explosion is so frequent that essentially you have a sort of continuous emission. Then, if you calculate the spectrum, the results are showing the following spectra that are ordered according to the time. So you start at the beginning with the blue, where there are only the stellar winds, and then you start exploding stars, and you see that the spectrum starts to fluctuate a lot, just because you are injecting some of the energy due to supernova. So the good point of the system is that the energetics is such that they can explain the total energetic of cosmic rays, but on the other hand, they show a strong intermittency. So the final spectrum is not as universal as in the case of a single supernova. Okay, so it remains an open question. So let's come to the last part of the talk. I'm just showing that young stellar cluster have been observed in the recent years. This is a list of the clusters that we know. There are almost 10. They are all massive. This is the mass in terms of solar masses. They are all compact, quite compact. And okay, there are also other quantities. Notice that the Sirius of B2, so the Sirius also called Sirius cocoon, has been observed also by LASO up to the energy of 1.4 PeV. So this is a strong indication that something interesting is going there. Those are few plots showing the morphology. The Sirius cocoon in Fermi, the Sirius cocoon observed by Oak, Western one observed by Yes, and then we have W40 observed by Fermi. This is just to show you that the morphology, even though we have only few objects, the morphology is quite complex. Okay, they show spectra which are quite similar, and also a profile, a weather profile that are suggestive of emission of cosmic rays from the interior that are diffusing away, even though Western one is not following this rule. The density of cosmic rays is showing a more flattened profile with a deep inside, which this is not surprising because in that case we are just assuming that particles are diffusing, but in this kind of system, also direction is important. The galactic center is another point which is interesting in the sense that it is possible that young stellar clusters that are located close to the galactic center could be responsible for the production of the spectrum that we observe, or the spectrum. We know that the spectrum is indeed showing is a pattern. And if you calculate the total cosmic luminosity that you need in order to produce the spectrum, and you also assume that the diffusion is somehow suppressed in that region, the power that you need is comparable to the power supplied by the the stellar clusters that are present in the region. With just the last two slides, how many subclusters are we expected to observe? This is a synthetic realization of the stellar cluster population with an age smaller than 10 megayears, so the mass between 100 and 60,000 solar masses. The total number of clusters is around 1,000, and the global one within 2 kiloparsec from the sun is roughly 70. The number that we actually have been detected in number is roughly 10. So there is plenty of numbers to increase the observed clusters, but there is a caveat. Those objects are very extended ones. If you calculate the size of the bubble, usually the typical size is of the order of a degree. So this means that if you observe with a typical Cherenkov telescope, the size it is a very so it is a diffuse sources. So it is difficult to detect, to distinguish between the backgrounds. In this plot, I'm showing the same synthetic population in data coordinate, and each circle is showing the size of the bubble. Now, if you make the same, you see that there are plenty of but if you now plot the same, you make the same plot in color code with the surface brightness, you see that many of them disappear just because the surface brightness is quite small, and so you end up with a smaller number of clusters. But even if they are smaller, we do expect the future Cherenkov telescope facilities to see many of those clusters. One trick to try to detect those clusters is looking for the emission from molecular clouds that are embedded inside the bubble. In that case, you enhance the emission. Okay, so I can leave you with my prediction, just saying that stellar cluster seems to be a very interesting class of object that can be responsible for the production of cosmic rays, I think especially in the highest energy part of the spectrum. Okay, thank you very much for listening.
Okay, Giovanni, do we have questions? Yes.
I think you talked about the composition anomaly of nails.
Yes.
And what is the energy range of nails which field that was anomaly?
Around the GV.
So does this mean that if the cluster solution to this problem, the clusters also must be dominant at this energy range?
Actually, no. If they were dominant at the energy of a GV, so that ratio would be much larger. So it is enough to have a fraction. This has been estimated in that paper by Yu, Gavici, also Tadic. It is enough to have roughly 10% at that end, 10% of contributions from stellar winds in order to explain the new 22 axis.
Do you expect any difference in the composition of cosmic rays that's in the cluster in respect to the supernova? Or what about the role of pulsars contributing to the cluster?
So you mean pulsars in terms of gamma ray emission from? So I guess that so for pulsars, I don't expect the contribution to be very relevant, just because those what we observe are very young. So you can have one or two pulsars, but only in cases there have been supernova exploding. But the cases that I was showing, they were essentially no supernova, so they are so young that there are no pulsars. So in that case, no. But for older clusters, this can be an issue. For the chemical composition, in general, you would expect the same solar composition with few exception. One is neon 22, the other is iron 60. I'm not sure, maybe for other chemicals larger, heavier than iron. But this is not completely sure, something that should be evaluated. Yes, there's another question.
So you're mentioning about individual sources as well, not just the contribution from the larger structures which can accelerate up to EV energy, but we also expect not large diffuse sources, but also point sources around the massive stars, like those blue variables.
You mean inside the cluster?
No, so just the individual stars themselves, like with just could we parse out not looking at the larger clusters, but just
So in principle, yes, but these can be only observed given the sensitivity of the instrument if they are very close. In principle, yes, but the point, let me go back to here. You see, those are all quite massive star clusters. And seeing of B can be observed because there are many clouds around. So the particle that accelerates just hit the particle. If you have an isolated system, essentially because you are accelerating the wind is very underdense with respect to the stellar medium. So the amount of cosmic ray is too low. Unless the system is close and you also have some clouds around the system. But in principle, yeah, there are so many that few of them can be observed. So another question. Yes, I can shout. No, you won't.
You basically explain in a few words the difference between the Western one and the others. They mentioned that it actually plays a role in this one, or the others.
Yeah. So actually, so for Western Lawn, yeah, there is a very recent paper by collaboration. Actually, this fits very well in the scenario where we are accelerated particle determination shock. And so you would expect an increase in the location of the determination shock. They're more or less a flattening because there you are affecting particle with the material which is affected inside the bubble. The others, so those are more close to be close to 1/r, but the analysis in those cases is quite tricky because while Western you see it's very so-called spherical. So the analysis is quite simple. There are not many clouds there. In the case of Sirius OP, for example, there are a lot of clouds. So here the analysis is tricky. So you have to determine correctly the amount of gas located there in order to infer the cosmic perspective. So my guess is that this result here is just the first order. If you go deeply, I would expect that you will not find a 1/r independent lift. You will find something flatter. This is my guess.
Maybe I can ask the last question, Giovanni. I was wondering about the authentic number of these termination shocks, right? With the parameters you quoted, magnetic field in excess of 10 microgauss, and with the mass loss rates with densities of 10⁻³ 10⁻⁴, somewhere thereabouts. So we'd expect our thing speeds on the order of 1,000 kilometers per second.
So yeah, it's usually larger than the solar normal in the solar medium. The Mach number is of the order of 10.
Yeah.
So not as powerful as supernovae, but still enough to be considered good accelerator.
Yeah, so what I was thinking is, in the end, there might be a constraint on certain regions in the parameter space where the authentic Mach number is actually only 3 or so, and then
yeah, you can happen. Because at the end, the density is that one, so you can fix the density because by the mass loss rate.
Right.
The magnetic field instead for for clusters that are only a few stars, you would expect a very low magnetic field because the amount of turbulence is smaller. So in that case, probably you have a sort of threshold. If you go below some total mass of a cluster, your Mach number of then drops down a few, and so there probably you are not able to accelerate anymore.
Yeah, it actually drops for high fields. So that's
right.
Okay, good. But that's maybe something for overtime as well.
Yeah.
Yeah, let's thank all the speakers. We do have the lunch break now, and please return to your panel session of choice in just the end.
So